Okay. I'll move the chair, and so we will talk about stereochemistry. So we discussed the fact that when you have an object in front of the mirror, if this is the mirror, and if you see the mirror image, sometimes if the mirror, if this is the object and this is its mirror image, they're identical. Like pretend that you're superimposing one into another. Basically, you're sticking one into another as if you're doing it on a computer screen. You're basically laying one on top of the other in a three-dimensional way. And what these two guys will do is they will basically synchronize. I mean, they will basically become one with the other. You can't distinguish. So a lot of times the object and its mirror image are identical, okay? For example, this guy and this guy, okay? This is a little, you can think about it like a tetrahedral carbon. You can think about it like a CH4 molecule. There's a carbon in the center, there are hydrogens, there are 4 hydrogens. So there also, imagine that this guy is looking into the mirror and sees its mirror image. And then the question is, are they identical or are they not identical? So if you're trying to superimpose one on top of the other, let me hold it against the white wall. When you're trying to superimpose one into another, you can tell that they do superimpose. This bond and this bond become the same. This bond and this bond, they become the same. These two bonds become the same, and these two bonds superimpose. So they kind of line up, okay? So when you have a methane molecule, another methane molecule, they are superimposable, okay? We will analyze that, and we will learn a few little tricks and a few definitions. Whatever we can cover in today's class, that's going to be fair game for stereochemistry. So I'm not trying to rush and pack more material. How many of you are there? 31, okay. I'll go with my reasonably.
Here's a result from search.
What? My phone is trying to talk. Whatever it is, what's that? It's not Siri. What's the name of the voice in Android? Cortana. Cortana heard me saying something. So it started talking. I'm going to shut it up. Okay. So when you have two methane molecules, this is the mirror image of this guy, and they're superimposable. Okay. So what I'm gonna do now is I'm gonna draw some few objects, right? Few objects, and show that there is some element of symmetry. When the molecule has symmetry, usually it's superimposable on its mirror image. When the symmetry is kind of broken, then it's not superimposable on its mirror image, okay? So I'm going to just draw something here. Okay, imagine this is, that doesn't look good. I have a problem with this. Let me change it. Imagine this is the hand of an alien with 4 fingers. I'll try to draw its mirror image on this side. So if this is the hand of an alien with 4 fingers, and if it is symmetrical, if the left-hand side and the right-hand side, this finger and this finger are identical, okay? If it is a really symmetrical hand, okay, left side and the right side are pretty much identical. It doesn't look like it, but know that they are identical. If they're identical, what do you think what do you think the relationship is? Do you think those two black hands with 4 fingers in each palm, do you think they're superimposable or they're not superimposable? Yes or no? Don't use the chat.
Yes.
They're superimposable, right? So they're superimposable means superimposable. That means these two objects are identical. Okay, they're identical, so they're basically same. On the other hand, when you have a hand like a human hand and its mirror image, okay, the relationship, if this is the thumb, it's a terrible drawing, so bear with me. That's the forefinger, this is the middle finger, that's the nail on the middle finger, that's the forefinger, index finger, this is your ring finger. Let's draw a ring. Then you know that's the ring, okay? The ring finger has a red ring on it, and that's your pinky, and it's got little red, green nail polish, okay? Left hand and right hand, the fingers, okay? When you try to superimpose, these two fingers have green nail polish. I've seen it, so I'm not coming up with some new ideas for fashion. I've seen you guys doing different colors on your fingers. I have eyes, I can see. So what's the relationship between these two hands? Are they superimposable or they're not superimposable? What do you guys think?
Not superimposable.
Not superimposable. Not superimposable. That means those two objects are different, right? They're not the same. That means they're not identical. Okay, my handwriting is becoming worse. Okay, so they're different objects. So similar deals can happen, similar phenomenon can occur with organic molecules. And we're going to start with an organic molecule as I started, methane. Hydrogen, 4 hydrogens around methane. And I'm going to build a couple of methane molecules, okay? And we'll go from there. So when you have a methane molecule, imagine this is the methane molecule, okay? The hydrogen on top is on the plane of the paper on the whiteboard. The hydrogen on the left side is on the whiteboard. This hydrogen is sticking out toward you, and that hydrogen is sticking away from you. Okay. For a second, I forgot that your vision is only up to this line. Okay. So I held it up. Sorry about that. So this is how the molecule looks like. So this guy's mirror image on the other side of the mirror, this is the mirror, is going to look like this. Let's pick up another one. Pretend that they're different. So this is going to be the mirror image, okay? Hydrogen up, hydrogen on the right side there on the whiteboard. This guy is sticking out and this guy is sticking behind, right? So these are the two mirror images, however you hold it. Let's hold it the way it's drawn here. These are the two methane molecules, okay? There is a lot of symmetry going on, right? There is a symmetrical plane that's cutting through this line, right? There is a plane of symmetry here. The left side and the right side are pretty much the same. There is a plane of symmetry here. The left side and the right side are pretty much the same. So there is a lot of symmetry in this molecule, okay? if you think about it, like remember what we talked about for a tetrahedral molecule, think about a cube, the carbon is in the center of the cube, these two are the two corners on the top of the cube, and these two are the two diagonal points at the bottom of the cube. And that's how you form a tetrahedral molecule, 109.5 degrees, 109.5 degrees, all the angles are 109.5 degrees. Okay, so these are the two methane molecules. One guy is in front of the mirror, another guy is inside the mirror. It's mirror image. What do you guys think about the relationship? Are they identical compounds? Are they superimposable, or they are not superimposable? Let's try. Let's try to like lay one on top of the other. If I try to lay one on top of the other, they kind of become one with the other, right? It sounds like a religious propaganda. Okay, saying that's a better word. So these two hydrogens, they kind of synchronize, they superimpose. These two hydrogens superimpose. These two hydrogens superimpose. These two hydrogens superimpose. So what is the relationship between a methane molecule and its mirror image? Are they same or different?
Same.
Same. So they're identical. Okay, sounds good. Thank you. So this relationship is, I'm just going to say SI for superimposable. They're superimposable, so they're identical. Okay, now let's start messing with the molecule. Let's start changing it. Let's just change one thing at a time. We'll keep the hydrogens. Let's put a fluorine here. Let's imagine that green is fluorine. Okay, and we're going to do the same thing on the right side. So when we have hydrogen, the hydrogen back is hydrogen, and this guy is a fluorine. Okay, so I'm going to switch it. I think I have green colored stuff that sticks, so I'm going to just switch it with a green. Okay, 3 hydrogens and a fluorine, right? So let's make another molecule, this guy, 3 hydrogens and a fluorine. These are the two compounds. This is this compound and this is this compound, right? Now, what do you think about their relationship? Do you think, let's name it. Can somebody name this molecule? CH3F. I know I have not taught you, but can you still do it? Fluorine will become fluoro, F-L-U-O-R-O. How would you name it? Speak up. I don't care about the chat. 1 fluorine and 3 hydrogens and a carbon. How would you name it? CH3F. How would you name it?
Fluoromethane.
Fluoromethane sounds good. That's it. Fluoromethane. Fluoromethane here and a fluoromethane here. This is the mirror image of this guy. On your left-hand side is the real molecule. On the right-hand side, it's mirror image. What do you think the relationship is? Are they superimposable? If I try to lay one on top of the other, do you think they will become one with the other? What do you guys think? Superimposable, they're identical, or they're different? Use your vocal cord, please.
Superimposable?
Superimposable? You're right. They're superimposable. The hydrogens lay on top of each other. The carbon is one on top of the other, and the fluorines are pretty much the same. So when you have this sort of situation, I'm just going to use different shape. They are also identical. Okay, this guy and this guy are identical even though they're mirror images. Now let's mess with them a little bit more. Now let's move to hydrogen, 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 hydrogen. Keep the fluorine. Keep the fluorine and put something else. Let's put a chlorine in the back. Okay, so what I'm going to do now is I'm going to switch one more element. I'm going to attach a chlorine here. Let's say chlorine is red. Let's say chlorine is red. So these are the two molecules, okay? This molecule, hydrogen, hydrogen, fluorine, and chlorine, and hydrogen, hydrogen, fluorine, and chlorine, okay? What do you think the relationship is? Are they identical? Can I superimpose one on top of the other, or I cannot? What's your gut feeling?
Yes,
No.
you can.
No.
Oh.
No or yes?
No.
No? Katie, no.
No.
Janessa, no.
Yes.
Juana, yes.
Yes.
Alina, yes.
No.
What about the guys? Now, are you afraid? Coral, no.
No.
No. Anybody else?
Yes.
Who is A?
No.
Okay, your name was just showing us A. Okay, let's try. I can superimpose there. So then, so the no answer is correct answer, or am I just messing with you? Animal? You got the answer. They superimpose. Green is with green, fluorine is with fluorine, chlorine is with chlorine, hydrogens are on hydrogen. So if you have two hydrogens and two other things, so three things attached to the central carbon, they're still the same. They're still superimposable. So the relationship between these two is still, they're superimposable and identical. Okay, now, obviously we are getting close to the climax. All right, let's put whatever group. I don't have any yellow, so yeah, we have purple. So let's use purple. Let's change this guy to, is iodine purple? Yeah, I mean, when we used to get cuts when we were in India, sometimes they would put some kind of an ointment with iodine that used to have a purple color. So fluorine, chlorine, and iodine. So let's change this molecule. Hydrogen, fluorine, chlorine, and iodine. We'll draw the same molecule on the right side. Hydrogen, fluorine, chlorine, and iodine. Okay, so this is this molecule, hydrogen, fluorine, chlorine on the back, and iodine on the top. Okay, I wish I could rest it here. I don't think I can rest it. Okay, I'll just hold on to it. On the right hand side, on the right-hand side, you have hydrogen on the right, iodine on the top, fluorine sticking out, and chlorine in the back. Okay? What I'm trying to do here is to show you that they are mirror images. You understand that, right? Because if this guy sees its mirror image in the mirror, on the right-hand side will be the fluorine in the mirror, right? Behind it will be the hydrogen, on top will be the iodine, and on the behind the mirror, on the back side will be the chlorine, right? So its mirror image will look exactly the same way, right? These two are the mirror images. The fluorines are mirror images. The hydrogens are mirror images with respect to the object. The chlorines are mirror images of each other, and the iodines are mirror images, right? So they are mirror images. So if I stand like this in the mirror, I will see my reflection. My right hand's reflection will be down there. My left hand's reflection will be down there. My right ear's reflection will be here. Left ear here. My face will be here. So you know what I'm talking about, right? Okay. So now the central tetrahedral sp3 carbon has 4 different things attached to itself: hydrogen, fluorine, chlorine, and iodine. What do you think their relationship is? Are they same? Are they superimposable, or they are not superimposable?
Superimposable.
Janessa, they're superimposable?
I agree too.
They're superimposable, so I can lay the purple on the purple, the green on the green, and the red on the red, and the black on the black. That's doable? That's possible? What do you guys think? Anybody else?
I changed my mind. I think it's not superimposable.
I'm going to say no as well.
Who is that other person? Janessa, and who else?
Ashley.
Okay, hi Ashley. Okay, so the 2 answers are no. I want to hear more. What do you guys think? Are they superimposable or not superimposable?
Not superimposable.
Okay, let's try. Let's try to line up the iodine and the fluorine. So I tried to line up the iodine and the fluorine, right? The purple, purple, and the green, green. Oops. The chlorine and the hydrogens are screwed up. Now let's try to line up the chlorine and the hydrogen. Chlorine and the hydrogens are lined up, but the fluorine and the iodines are screwed up. So no matter what you try, let's try the black and the purple. Let's try the black and the purple. The other 2 are not lined up. So where are we heading? When you have 4 different groups attached to the central tetrahedral carbon, that molecule is not superimposable on its mirror image. Okay? So they're kind of like our left hand and right hand.
That will make it isomer, right?
Getting there. So when you have a situation like this, completely different environment around the carbons, the central carbon, they are not superimposable. So they're not same. These guys are not same or identical. They're completely different beasts. They're very similar, right? You know that your left hand and right hands are almost same, but there is something different. Would you shake hands with somebody else with your left hand if it was not a social taboo? Like if somebody doesn't mind which hand you stretch to that person, but would you really stretch your left hand when someone is, giving you his right hand? No, because you know that it doesn't work. But you might think that my hands are same, they're identical. Now you know your hands are not the same, your ears are not the same, your eyes are not the same, they're different, right? So the interaction, your left shoe only fits in your left foot, your right shoe only fits in your right foot, your left mitten fits only in your left hand, right mitten fits in your right hand. Similarly, you know, some caps only go in one way, right? Your socks and everything else. So when you have two sp3 when you have one sp3 carbon and two compounds, and that sp3 carbon has 4 different things attached to itself, and when you are looking at the mirror image and the original molecule, the relationship is they are not the same compound, and those are, you're right, whoever mentioned it, I forgot who that was, they're isomers. What kind of isomers? That isomer definition is called, does anybody know? It's an E word. Have you read the book yet?
No, sorry, because I was just going through with my letter opener.
Can't hear you.
I didn't look to see what it was.
Be a little bit closer to the microphone. They're called enantiomers. You need to memorize that word. They're called, I'm going to write it down in red. They're called enan, tio, enantiomer. The relationship between two compounds that are not superimposable and their mirror images, that relationship is enantiomer. So these guys are enantiomers. Enantiomers. My 2 feet are enantiomers. 2 shoulders are enantiomers. So if an object is not superimposable on its mirror image, they're called enantiomers. I can't fit that definition anywhere here. So I'm going to take a snapshot of the board and I'm going to write that down again, and we're going to analyze these molecules a little bit longer and discuss something else that might give you some vertigo. Hopefully not. So let's take a picture of the board. Okay. I won't pause very long. I might pause for just 15 seconds. Okay. So as you can tell, that when 2 things are identical, before we switch to the iodine, while we were still holding on to this situation, right? This guy and this guy. This molecule, right? You can tell that there is some symmetry. Where is the symmetry? You might say, where do you see symmetry? There is symmetry. Think about this plane. I'm just trying to look for like a flat surface. If you think about this plane, the plane that contains, that are holding on to the chlorine and the fluorine, you can think about this plane, you can see that this is a symmetry plane, because the left side of the plane and the right side of the plane are identical. There are 2 hydrogens, right? And the plane itself holds on to these 2 objects, the fluorine and the chlorine, right? So the fluorine and the chlorine are on the plane, and this is so there is still a plane of symmetry. The moment you change it to an iodine, okay, whenever I can figure out how to do it, the moment you change it to an iodine, I did it wrong. Okay, so this molecule, whenever I change it to an iodine, whenever I change this guy to an iodine, so that will be, this guy. Whenever I change this molecule to an iodine, so now they're mirror images. Okay, the last molecule that are not superimposable. You can tell that they're not superimposable as we try to superimpose one on top of the other. They're not superimposable. Now you can tell there is no plane. There is no symmetrical plane. There is no symmetrical plane, because if I say that there is a symmetrical plane here, well, you can tell that right side is fluorine, left side is iodine. It doesn't work. If you have to have a symmetrical plane, the left side and the right side must have identical objects. If I say that this is a symmetrical plane, then left side and right side must be the same thing, but it's fluorine and chlorine. That doesn't work. If I say that this is a symmetrical plane, black and the red, then the two sides are different. So you can see that we have really murdered any symmetry that was present in the earlier molecules. This guy had a lot of symmetry. This guy had quite a bit of symmetry. This guy has one symmetrical plane going through the fluorine and the chlorine and the carbon. This last molecule, there is no symmetry whatsoever, okay? So that's the problem. Symmetry and enantiomers, they kind of go hand in hand. And why this is important? Because this is very important. Imagine this is a molecule. If this cures cancer, this might do something completely different, because as they enter into our living system, in our living body, they might interact completely different with those figures, with the different objects, different proteins, different DNA, RNA. Their interaction may be completely different, because you know that your right hand binds one way with somebody else's left hand and binds differently with somebody else's right hand. Right and left hands interact differently with the right or left hand. So if you throw your right hand, imagine you make a drone, okay? You make a drone that has a human hand to shake hands with people, okay? And if your drone has a right hand, it's going to interact in certain ways with a bunch of people in a concert. It's going to only shake hands with people's left hand. If you make a drone with a human hand that looks like a left hand, it's going to interact differently with that same 100 people present in that concert, because it's going to probably make people more uncomfortable, because the left hand will demand people stretching their left hand to shake hands. So you can actually do an experiment. If you make a drone with a left hand and if you make a drone with the right hand, which drone will be more accepted by the mob for doing like a artificial handshake? Not now, after all this is over, right? You get the point. So this is very important. So I took a picture. I'm going to erase it and then talk about something else. 15 seconds. You can ask questions if you have any questions. I'll see how to handle the questions. But this is something that will really, you will really appreciate having a model with you, because this is not something that you can imagine. Some of us are good with imagining three-dimensional objects, some of us are not. Buy a model even if it's pretty late. Okay, you can buy like a $12 model from eBay or Amazon. Okay, I'm assuming there is no question. So I'm going to erase the board and I'm going to have like a fake mirror in the middle and write down the definition of enantiomers. So let's imagine that this is the mirror. Okay. That's the mirror. And the definition of enantiomer, let's write down the definition of enantiomer. Enantiomer definition. When an object is not superimposable on its mirror image, the object and the mirror image are enantiomers. Okay, that's the definition. When any object is not superimposable on its mirror image object, then their relationship between them is they're enantiomers. Okay, when it comes to real molecules, in order for this to happen in an organic molecule, the organic molecule must have, that's a have, sorry, must have number four different, let me write it down with a different color. The organic molecule must have 4 different elements or groups around tetrahedral carbon. Okay, so the bottom line is, I'm going to write it down. Tetrahedral carbon means sp3. So there has to be, in the whole darn molecule, there can be just one tetrahedral carbon. And if that tetrahedral carbon has 4 different things attached to itself, then it's not going to be superimposable on its mirror image. And then those 2 molecules, their relationship will be enantiomers. It doesn't work for sp2. It doesn't work for sp hybridized carbons. It must be sp3, and the sp3 carbon must have 4 different groups attached to itself. Okay, so we can do like a little analysis. So imagine this. Let's draw it here. So this is still the mirror. This is still the mirror. And left side is the shiny side. So imagine this molecule. This is the molecule and this is its mirror image. Ethane and ethane. So you could have drawn it like this, like a hyphen, right? So when you have a hyphen on the left side and a hyphen on the right side, CH3, CH3 on the left and CH2, CH2 on the right, do you think they're enantiomers? They're superimposable or not superimposable? What do you think? What is the relationship between 2 ethane molecules? Ethane molecule 1 and its mirror image, ethane molecule in the mirror. Are the same or different?
They're the same.
They're the same, right? So they're same. Okay, now I'm going to draw a molecule a little in a little tricky way. So the relationship between these 2 molecules. Name the molecule first. You guys have learned it. Like a propeller ship molecule, CH3, 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 and in the middle they have a CH. How would you name this molecule? Who can name it correctly? There is pressure on you now. Not just any nonsense name. What's the name of the molecule? Longest chain. Find the substituent. Name the molecule. If you have to number it, number it. Come on, guys. What's the longest chain?
Butane.
Butane. How many carbons does butane have? 1, 2, 3, 4. This is not butane. 1, 2, 3. That's what?
2-methylpropane.
I know who that is. I don't. You don't even have to tell me your name. I know that you love nomenclature. So maybe you can. You don't answer somebody else. What's the name of the molecule? What's the longest chain? When I heard what you said, and it's correct. What's the longest chain? Everybody minus when in.
Couple.
Sorry? Propane. Okay. So it's some kind of propane. What kind of propane is it? What's the functional group called?
Methyl.
Methyl. So what's the name of it? When in, can you not answer? Thank you.
Methylpropane.
Sorry?
2-methyl.
2-methylpropane. Yeah, 2-methylpropane. So there is 2-methylpropane here and 2-methylpropane here. Do you think they will be there? They look like mirror images. Do you think they are superimposable on each other or not?
Yes, they're the same.
They're same. Because what's the rule? The rule is that the central carbon or one of the sp3 carbons must have 4 different things. This guy has 3 methyl groups. It doesn't cut it. It doesn't satisfy the rule. So they're same. Same or identical. They're superimposable. How about now? This molecule What about this molecule and that molecule?
They're the same.
Read the definition before you jump to a conclusion. So we are analyzing this guy. We are analyzing that carbon. Okay? If we're analyzing that carbon, what's the definition for an organic molecule to be an enantiomeric? The organic molecule must have 4 different elements or groups attached to one's central carbon. Analyze this carbon. Is it attached to 4 different things? No. Is this carbon attached to 4 different things? No. None of these carbons are attached to 4 different things. But how about the red carbon? The red carbon, analyze it. What is the red carbon attached to on the left side and the right side? What is it attached to? It's attached to a hydrogen, right? It's attached to a methyl group, right? It's attached to an ethyl group, and it's attached to a propyl group. Isn't that red carbon, tetrahedral carbon, isn't that carbon attached to 4 different things? Yes or no?
Yes.
Yes.
Thank you, Adamina. Okay, so those red carbons are attached to 4 different things. And that's definitely the mirror image of this guy, because the ethyl group is on the right, down on the plane. The propyl group is on the plane down here, and looks like a mirror image of that. They're both pointing in the same direction. The hydrogen is sticking behind the whiteboard on both sides. They look like mirror image. And the methyl group is sticking out here, and the methyl group is sticking out there. Ethyl is on that side, ethyl is on that side, propyl is on the left, propyl is on the right. So they look like mirror images, and they look like that central carbon has 4 different things attached to itself. Therefore, what do you think will happen if I make a model, if I had the time to make a model of each of those compounds and try to superimpose one on top of the other? Do you think I would succeed, or do you think I will have an epic failure when I'm trying to superimpose the 2 compounds? Can I superimpose them, yes or no?
No.
Thank you. So these 2 compounds are not superimposable. Therefore, what is the relationship? Read the definitions. What is the relationship between the 2 compounds? What kind of isomers are they?
Enantiomers?
Enantiomers. They're called enantiomers. Okay, so that's how you look for it if you see it in the quiz or in the test or in the final, in the exam. You need to analyze each carbon. 3 hydrogens, no way this is an enantiomer. It can make the molecule enantiomeric. This carbon has 2 hydrogens, so 2, same thing. The carbon must be attached to 4 different things: fluorine, chlorine, bromine, iodine. Hydrogen, fluorine, chlorine, iodine. Hydrogen, ethyl, fluorine, and bromine. 4 different things. That's the bottom line. It must be attached to 1 carbon in the molecule, must be attached to 4 different things. And that's the only way that molecule is going to be non-superimposable on its mirror image. And then the relationship will be enantiomers. I'm going to take a picture of the board. So what I'm going to do now is I'm going to erase everything except for those 2 compounds, and I'm going to teach you guys something else. Okay? Listen to the videos. Now you have access to the video for endless amount of time until the end of the semester. So listen to the videos over and over, look at the pictures over and over, and make sure that you understand what's going on, okay? The amount of material that will be taught to you guys is going to be significantly less than a regular semester. And I was just thinking about that, and I feel bad, but there's nothing I can do about it, okay? So what I'm going to do is I'm going to redraw the molecule up here and teach you a trick by which we can label 1 carbon over the other. I'll teach you something now, okay? I'm going to use the different colors. The colors that I've used to like circle the molecules, I'm going to use those colors. So let's draw the mirror again. Where is the mirror? Here is the mirror. That's the mirror. Let's draw this guy pretty big. So that's carbon, the central carbon, okay? The hydrogens are in the back. The hydrogen is in the back. The methyl group is out in the front. That's the methyl group. The ethyl group is on the left side on the plane of the whiteboard. Plane of the whiteboard, and whatever the color is, orange, I guess. That's the propyl group. Okay, now I have the courage to delete this molecule. It's the same compound. Okay, now it's very much possible, it's really, I'm not kidding, it's very much possible that 1 molecule will interact one way if I take 10 milligrams of the left molecule versus I take 10 milligrams of the right molecule inside my body, and they interact with some protein and do something, which could be a good thing or a bad thing. It's totally possible that this could make me remember all my childhood mischiefs, and that guy could grow a tumor in the back of my head. I'm not kidding, it can happen. I do not know what will happen with these specific molecules. What I'm trying to tell you is that, let's say this turns out to be a drug candidate for our Alzheimer's disease project, okay? Let's say this is the molecule that seems to be doing a pretty good job as far as cleaning up the plaques in the Alzheimer's patients. It can very well happen that this will do the right job. This might not do anything. Okay, it may not do any harm, but it may not do any good either. So the right and the left molecules might do completely different interactions, set of interactions, once it's inside other like less symmetric species. Proteins are made out of one type of molecules, lefty or righty. So they're all going to interact with the two molecules, the left hand and the right hand. Remember the example that I used, drone with the right hand and drone with the left hand. They're going to interact differently in a concert with different people. They're going to either draw attention in a positive way or may not draw any attention in a positive way, maybe neutral, or people might hate it when they see a left hand with a drone hanging down and it says, "Shake hands with me," something like it's popping up on a little screen. And if you see a left hand, you're like, I don't know how to shake hands with my left hand. I'm more comfortable with my right hand. So it might annoy people. But if you see another drone coming down with the right hand, it might be much more well received. So same thing can happen. So the bottom line is, this is one species and that's a completely different species, like your left hand and right hand, right? So there must be a way to label this species. We must figure out a way that this is this and this is that. So let's say we are collaborating with a group in South Korea or in Afghanistan or wherever, okay, another group. And if this is what we want, we need to tell them that, guys, make sure that you don't screw up. You don't send me that molecule, you send me this molecule. So how do we do it? I mean, if we cannot send them a picture, then we have to figure out a way to send them just a text without a picture. So how do we tell which molecule is which? So there is a convention to call them two uppercase letters, R or S, based on the orientation of the different groups. How do you do it? Well, this is how we do it. We need to learn it today. So the carbon, so first thing first, their relationship is enantiomers. These two guys are enantiomers. They're isomers. What kind of isomers? Well, they're enantiomers because they are mirror image, non-superimposable. That's why. Okay, we just learned the definition. They're enantiomers. Okay, now the carbon that's the culprit, that's breaking the symmetry and causing this enantiomer business, that carbon is called a chiral carbon. Okay, and oftentimes the carbon we put like a little asterisk. Okay, we put an asterisk on the carbon that's attached to 4 different things. In a big molecule, there may be like 500 carbons, but only one carbon, suits this definition because it's got 4 different things attached to itself. And that's the carbon that gets an asterisk. And we call that carbon a chiral carbon, C-H-I-R-A-L, chiral carbon. Chiral carbon means 4 things attached, 4 groups or elements attached to it. Okay? Now, which one is which? I told you that we have a convention to label them uppercase R or uppercase L. So we use this definition. We call one of them R and we call the other guy S. And they're always mirror image of each other. Okay, one is R and one is S. So what's the definition? How do you, which one is R? Is this molecule R, this molecule S, or this molecule S, this molecule R? Okay, this is how you do it. find the chiral carbon, find the 4 different things attached to it, and kind of put like weightage numbers. Like, okay, be careful here. The book does it with 1, 2, 3, 4. I don't like it. But if you like 1, 2, 3, 4, stick to that convention of 1, 2, 3, 4. 1 being the smallest group, 2 the larger group, 3 the larger, 4 the largest. The way I like to do is extra small and then small, medium, large. That makes me hungry, but I can't help it. So the smallest group is going to be extra small, and the other groups are going to be large, medium, and small. That depends on their atomic number or how many carbons, how many hydrogens are attached. I'm going to keep it very simple for you guys for the rest of the semester. It's going to be very obvious. I'm not going to try to trick you, okay? So one group is hydrogen, one group is methyl, one group is ethyl, one group is propyl. So tell me which group should be extra small.
Hydrogen.
Thank you. So let's use a new color. Let's use this purple color for labeling them. So this is extra small. I just wrote X and S. So this is extra small. Okay. Which group is small? Which group is medium? And which group is large? Which group is small?
Methyl will be small.
Small. Which
Ethyl will
group
be
is
medium.
medium?
And then propane will be your large.
Yep. So let me just circle them. Maybe that'll make it look a little bit more prominent. Okay. Now, the way you draw the three-dimensional molecule in 3D, because you know that it's a chiral molecule, and how you put them in space is important. The hydrogen is back for this molecule, methyl is out, hydrogen is back, methyl is out, but something else is different for the molecule on the left and molecule on the right. The ethyl
They
is on the
rotate a
left.
different direction.
Yeah, the green ethyl group is on the left, green ethyl group is on the right, and whatever color this is, like let's say orange propyl is on the right, orange propyl is on the left. Now what you do is you have to always make sure that the extra small group is drawn with the dashed line. The extra small guy, where is my blue? Right there. Okay. The extra small must be like this, sticking back. Okay, then what you do is you move from large to medium to small. Okay, like as if you're jumping like monkeys. Okay, I'm sorry, I'm stuck with the monkeys. Large to medium to small, and see what direction that is, clockwise or anti-clockwise. Okay, extra small is in the back. This is your large, this is your medium, and that's your small. So when you're traveling from large to medium to small, and small to large, when you're going in that circle, large to medium to small, this is very important. How many pens can I hold in my hand? Large to medium to small. As you are traveling from large to medium to small, if that rotation is clockwise, we call that chiral carbon R. Is this clockwise or anti-clockwise?
Clockwise.
This is clockwise. So if this direction is, this movement is clockwise, we call it R. What color did I use? Black. So if this is clockwise, this guy is R. Over here, large to medium to small, large to medium to small is anti-clockwise. Over here, it doesn't look like it's clockwise. This is anti-clockwise. If it is anti-clockwise, then we define that chiral carbon as an S carbon, uppercase S. Oops, wrong color. Then we call it S. Okay, so this is how you define R enantiomer from S enantiomer. I'm going to shut up for like 50. I just hurt myself. Some people never learn. I'm one of them. Shouldn't have done that. Okay, I'm going to take a picture. This is important, guys. Okay, what have we learned? We have learned quite a bit today. We still have 10 more minutes. We have learned two objects, an object and its mirror image, when they're not superimposable, that their relationship is called enantiomers. That's some kind of the isomer, as you guys pointed out. So they're isomers. What kind of isomers? They're enantiomers. So left hand, right hand, left foot, left eye, right eye, blah, blah, blah. They're all enantiomers. When can a regular, like a normal, like a molecule become enantiomer with each other? When one carbon. What kind of carbon? Can sp carbon do it? No. sp2? No. It has to be an sp3 carbon. When an sp3 carbon is attached to 4 different groups or atoms or whatever it is, then that guy and its mirror image, and remember in these cases you have to use the solid lines, the wedge, and the dashed line to describe which one is which. You cannot get away drawing them in bold lines because that means nothing. If you draw them flat, which one is which? You have no freaking clue. You have to draw them with the wedge, dashed line, and 2 solid lines, right? Solid, solid, wedge, dash. Solid, solid, wedge, dash. Unless you do that, you can't win this chapter or win this material. Okay? When you do that, and then they are enantiomers in the 2 sides of the mirror. Then we learned that there is a way to kind of label each of those carbons. Those carbons are called chiral carbons. A chiral carbon makes that molecule enantiomer with its mirror image. And the 2 chiral carbons can be labeled differently. Like ibuprofen has a chiral carbon. Acetaminophen doesn't have a chiral carbon. Tylenol doesn't have a chiral carbon. Aleve has a chiral carbon. Aspirin doesn't have a chiral carbon. For ibuprofen, it's the S isomer that actually takes down our inflammation. When I have my hand flaring up, when I don't follow the rules, when I try to like catch a dropping pen and it hurts, I take that medicine. So the S enantiomer is the right enantiomer that takes down my inflammation and takes care of my fever and my pain. The R enantiomer, thank God, it doesn't do anything bad, but it doesn't do any good. It's just there, sitting there doing nothing. Okay, so it's very important. So ibuprofen, one molecule is good, the other molecule is pretty much useless. You know, like many teams, like team of 18 people working on a drug discovery project, maybe 3 of them are actually doing good. The rest are like freeloaders, just going for a free ride. Okay, did I take a picture or not? I don't remember. Maybe I did, maybe I didn't.
I don't think you did, Professor.
Okay, there you go. I took a picture. So you guys need to watch this over and over. This is very important. I'm going to draw another molecule. I should have done it earlier. It doesn't have to be different groups of different sizes. Let's draw another molecule and analyze their relationship and the whatever this is called. So let's draw a central carbon with black. Black and black. Let's put, I'm going to, for your benefit, I'm always going to put the extra small group in the back. I'm not going to mess with your mind and make it worse than it has to be. So I'm always going to make that hydrogen in the back, which is going to be dashed line. Okay, that's that. Now, what I'm going to do is I'm going to put iodine here, iodine here, a bromine here. Don't follow the color coding. Bromine is usually red, but then you understand. And fluorine. Fluorine. Okay. So between these two compounds, my first question is, what is the relationship between the two compounds? You have to kind of process it in your brain, going through the different stages. What is the relationship between that molecule and that molecule? Each molecule has 3 halogens attached to itself: a bromine, a chlorine, and a fluorine. Bromine, iodine, and fluorine. What is the relationship between them? One on the left side of the mirror, one on the right side of the mirror. Speak up, please.
They're not superimposable.
They're not superimposable. Fantastic. That means they're what?
Enantiomers.
They're enantiomers. Okay, very good. Excellent. So they're enantiomers. I'll take another picture of this board. Okay, enantiomers. This guy on the left side, let me just not tell you how to do it. I want you to kind of figure it out. Which one is R and which one is S? Let's look at the left molecule. Is this molecule R or is this molecule S? How do you do it? Who is your extra small group?
Hydrogen.
Who is your large? How do you go about it? It's not the size here. What group?
Iodine, so your largest group.
Sounds good to me. And who is your medium?
Floral.
No, fluorine is on the top. Fluorine, chlorine, bromine, iodine. Iodine is the largest, then bromine, then chlorine, then fluorine. This is
Are we going off? I understand it, but because are we going to use their atomic number or their atomic weight to determine which
atomic
group?
number.
Oh, you know what? I'm looking at bromine and not bromine. Sorry, that's why. Yeah. So medium would be bromine, and then fluorine would be small. Sorry, I was looking at the wrong one.
That's fine. No problem. What direction is this?
That's our group.
If this is R and that's the mirror image, don't waste your time. It has to be S. S is always a mirror image of R.
And when we're comparing the atomic mass, right, and not the atomic number, or it doesn't matter?
Atomic number is good enough.
Okay.
So you use atomic number, but in this case, the atomic number doesn't work, right? This is a carbon, this is a carbon, this is a carbon. At that time, you look for which one is bigger than the other, okay? So we kind of the atomic number doesn't work here. Atomic number works here, so whatever works here, okay?
So on the top one, we would look at atomic mass basically because we will be adding the two.
Not atomic mass, but then the total mass of the molecule, not atomic mass. That's going to be very confusing. Atomic mass of carbon and atomic mass of carbon is same. The group mass, the weight or the size of the group. This is CH3. Carbon is attached to 3 hydrogens. Here,
That one has 2.
2 hydrogen and a carbon. Here, the carbon is attached to 2 hydrogens and a carbon, but the next carbon is attached to another carbon. Next carbon is not attached to another carbon. So you just use your best judgment. If you look at them, you can probably tell that methyl is smaller than ethyl, ethyl is smaller than propyl. So use your best judgment. Okay, so let me take another picture of the board because I added that molecule. So this is important. We have 4 minutes, okay? Since this is being recorded, I'm not too worried about you guys not getting the concept. What I would like to add, I'm just going to erase everything except for the top molecule. I'm just going to erase the bottom molecule. Maybe it will give you like 10 seconds to grasp it. We learned how to do R and S of the enantiomers, left molecule and the right molecule. So that's a very important skill, and that's you're going to be judged on the basis of your understanding and capability to reproduce it in the exam. How to figure out R and S. Find out the smallest group, large, medium, small. The book does it in a different way. 1, 2, 3, 4. Then you go from 4 to 3 to 2. This is more easy for me. Okay, I'm just going to erase this molecule, and I'm just going to mention something. Like what physical property difference do these molecules have? The left molecule and the right molecule. This is R and this is S. Pretty much their melting point is the same. Their boiling point is the same. Their flash point is the same. They look pretty much the same way. They're almost every physical property is identical for the enantiomers. Only one thing is not identical. I don't know if we can pull it off, but let's see if I can pull it off in 2 minutes. You know that when you have light is like an electromagnetic wave. So when you are seeing me, because light is getting reflected off my face and glasses and everywhere here, and the light is coming toward you in a wavy fashion, like a wave. Okay, usually, okay, this is going from left to right. When you look at it head on, this is the side view of light. Okay, when you look at the light wave from the front, if you put your eye here, and if you look at the light head on, lights are coming like vertically, they're coming horizontally, and in every angle. Okay? If you pass this light through a slit, through a vertical slit, okay, what comes out of that vertical slit on the other side of the light, side of the vertical slit, is only the light that's going vertically. Okay, and that light is called plane polarized light. This is called PLANE, polarized, POLARIZED, plane polarized light. So what does plane polarized light have to do with enantiomers? Well, the only thing that's different about enantiomers is the following. When you have enantiomers, when you have plane polarized light and it's going through the R compound versus the S compound. As it passes through an R compound, plane polarized light, vertically plane polarized light, and when it comes out of that molecule, okay, and when it comes out from the S molecule, something happens to them differently. And that's how you can tell that you're dealing with the left molecule versus the right molecule. What do you guys think will happen? I might take like an extra 1 or 2 minutes. As it comes out of the R molecule, something happens to this vertically polarized light, and something happens to the same light when it goes through this molecule. What happens? That can tell you that they're different, passing through different compounds. What do you guys think? Make a wild guess. How many of you are still there? 32.
It could change the direction, like the orientation of the light.
Yep, let's say the light goes in vertically and it comes out of the R molecule, and this is how it was, but now it's tilted to the right by, let's say, 30 degrees, alpha degree, not centigrade, whatever that angle is. So when it comes out from the S molecule, it tilts to the opposite direction, which is extremely fascinating by the same angle, alpha degrees. So the R enantiomer tilts plane polarized light to one direction. It doesn't have to be right or left, whatever direction, but you know for sure that the S isomer will turn it in the wrong direction. So I'll just write it down. Enantiomers turn plane polarized light to opposite directions. Okay? If R enantiomer turns it to one direction, S enantiomer is definitely going to turn it the opposite direction. So that pretty much brings us to the end of our lecture today. Read the announcement. I don't want to discuss it now. Read the announcement carefully, and then we will have another lecture on Wednesday, and another lecture on Monday, another lecture on Wednesday, and then read about the quiz and read about the test. I think it's not the end of the world, but if I asked you guys that if you have any problems, email me. If you don't have any problems, don't bother emailing me. Okay?
So that plane of polarized light, it kind of mimics like the concept of a microscope. Is that what I'm trying to?
Not really. There is a
No, because I know a microscope, it goes reverse, but then it just changes the whole
it's
thing.
kind of like you're talking about how polarized things look differently, right?
Yeah, because you're saying it rotates, so I'm thinking it's kind of like a microscope.
It's kind of
Similar?
some of the transition lenses on our glasses, the coating, they deal with polarized light. When we talk about some sunglasses deal with polarized light in a certain way. So this light means that you have filtered off all the light waves that were going horizontally at an angle, at this angle. You're only allowing the light that was coming in vertical wave form, okay? Because you just like cut like a little slit in a piece of paper, and whatever light came out from the other side of the paper, they're only going up and down vertically. So when that light enters into this molecule, let's say it tilts to the left. When the same light enters into this molecule, it tilts to the other direction. So by looking at which direction it tilted, you can tell, oh, I'm dealing with one molecule, one enantiomer, left or right. And then when you see the other direction tilting, then you can tell that you're dealing with another molecule. When it's supposed to tilt by 30 degrees, but it's tilting by less than 30 degrees, then you know that it's probably mixed. So you can do all kinds of mathematical calculations and stuff.
Okay, thank you.
No problem. Any other question? You are staying longer than you have to, but then I don't mind answering your questions if you want to ask any questions. Already down to 18. Read the announcement, please, and give me feedback. If you have any problem with that, I may not be able to do it that way. Okay. All right. Any other questions? So I'm going to switch to the front camera and see if anybody has any questions. Otherwise, we will see you guys on Wednesday. All right. I'm going to end the meeting. Okay. Take care and have a good day, and see you guys on Wednesday. Be safe and be happy. Bye, guys.